Our second speaker is Soumyadip Sarkar, who's a doctoral student at the Institute of Mathematical Sciences. He had a different title, I think. But anyway,
yeah,
there is.
Yeah, thanks to the organizers for the opportunity. So I will talk about the restriction problem in algebraic combinatorics and its connection to this Kashiwara crystals. So just to recall some basic definitions, polynomial representation of GLN-C is a group homomorphism from GLN to GLM, so that the matrix coefficient are polynomial functions in the entries of G, and irreducibles are parameterized by, so irreducibles of degree D are parameterized by partition of D with at most n parts. And this is well known that the character of this modules are given by Schur polynomials, S lambda into n variables. So now this group of permutation matrix so sits inside GLN-C. So Sn sits inside GLN-C. And we know that irreducibles of Sns are parameterized by all partitions of n. And we are interested in this restriction problem that you take a while module, this irreducible while module W lambda GLN-C, you restrict it to Sn and how it decomposes as Sn module. So we are interested in the multiplicity of this restriction. V mu is the Spech module for Sn. The question is that can you find a positive combinatorial description for R lambda mu? So that is a question of interest. So this is one new perspective to study the restriction. So adapting the idea of Mackay, so Narayanan, Digjoy, Amritanshu and Shraddha, they define that induction functor. So you start with a representation of Sn, and then you can define this vector space in dV, which are basically the space of all degree D V valued homogeneous polynomials, so that f transforms under this rule, f of wq is equal to rho w dot fq. So basically remember rho is the given representation of Sn. And now the point is that this GLN-C acts on this in dV via this right translation. G dot fx is equal to f of xg. So this in dV is actually in fact a GLN mod. Okay, so I think in this talk, so even for the trivial representation of Sn, the combinatorial description is not yet understood. I mean the restriction coefficients are not well understood. So here is a way to think about this in D GLN Sn trivial. So basically you take the trivial of Sn in D CT GLN, and what is the space? This space is just the space of all homogeneous polynomial functions of degree D which are invariant under rho permutation. So that is given by this f of wx equal to f. And so they proved that Frobenius reciprocity holds in this framework. So if you restrict the while module to Sn and you ask for the multiplicity of V mu, that is same as asking you start with the Spech module V mu for Sn and induce it to GLN and ask how many times is W lambda occurs. And actually one good thing about this perspective is that from this perspective, one rediscovers the plethistic formula of Littlewood. So Littlewood gave this formula that R lambda mu is given by the Hall inner product of S lambda and S mu plethism capital H. So maybe I should write what is capital H. So S lambda is the usual Schur function, but capital H is just this thing. So you take sum of all HD, where HD is the complete symmetric function of degree D, and you take sum of all of these. So this does not exactly lie in the ring of symmetric function. It lies rather in the completion of symmetric function. So, and Littlewood had this formula that R lambda mu is actually given by this plethism. So no satisfactory combinatorial interpretation is known for this. So however, Narayanan gives some interpretation for some special cases where lambda is a hook partition and the round bracket n just means the trivial representation of Sn. And for sign representation, that too when either lambda is a 2-row or 2-column partition. Only in very few cases the combinatorial interpretation is known. So even this question is hard. So can you classify all lambda so that when you restrict W lambda to Sn, it admits some invariant vector? Maybe you do not, you cannot tell the exact multiplicity, but at least can you say something about the positivity? So to study this thing, I sort of defined this refinement of the induction. So earlier remember I defined this in D, this induction functor from rep Sn to rep D GLN. So I will define sort of a refinement of that. So for that, okay, I will just introduce some notation. So suppose X is a matrix in GLN C and I have the monomial polynomial function Xij to the power Aij. I will just denote that by the matrix, round bracket matrix Aij. For example, this 2, 3, 1, 4 would mean we're looking at the polynomial function x11 square, x12 cube, x21 to the power 1, x22 to the power. And so since just look at this definition, so these are basically all functions which are invariant under row permutation. Right? So that is why a basis for this in D GLN Sn1, that is just parameterized by set of all matrices whose entry sum is D, but modulo the permutation of rows. So that is a basis for this. And exactly we will target this set to define the crystal structure. So that's what we are hoping for. Okay. So for example, I will denote the symmetrized version of 2314 by the square bracket 2314. So the square bracket 2314 just means 2314 plus 1423, where 2314, the matrix just denotes the monomial Xij to the power Ai. Just a notation. Now one thing is that, so this GLN acts on this induction space by right translation. So one can differentiate this to get a Lie algebra action, and I will just say why that perspective is important, because that helped me to guess one particular thing. Yeah, so if you differentiate the action, so you precisely get this action, that when your diagonal matrix each acts on the monomial x to the power a exactly by this, and ei acts on this by this formula, and if I acts by this formula. So maybe I'll just give an example. I think the example is, yeah, this is the example, just in the 2 by 2 case. So the action of the diagonal matrix is given by this, and the action of E is given by that thing. So basically, you always take one from the second column and move it to the first column. That is what, and some coefficient also comes in this process. So this is the differentiated action of Lie algebra. Okay, so now I will define this thing, that this refined induction. So I'll refine this in D functor with a further refinement parameterized by a partition of D. Okay. So this is also just, I mean, yeah. So if I take a matrix A, I look at the row sums. And I sort them in decreasing order, I get a partition. So that is the first process. And then, since, please observe this thing, that under the action of the Lie algebra, the row sum does not change. The row sum does not get affected when we apply the E's and F's. So from that, you can say that this Sn invariant polynomial solve GLN with a fixed sorted row sum, that is actually a submodule of this in D GLN Sn. And exactly this module, we denote it by ind mu D GL. And it is then it is easy to see that this induction space breaks up into these pieces. where this this mu's are partitions of D with at most in part. And now the interesting thing is that if we look the character of each piece, this ind mu D is given by this formula. So what is this formula? So you write mu in the exponential notation. So 1 occurs m1 times, 2 occurs m2 times, and so on. And then the character of this sum module is exactly given by product of this sort of plethisms. So I'll just shortly explain what is plethism. So you can just think of, you take the standard representation of GLV, GLV acts on V. So HM plethism HN is just the character of sim M of sim N of V. So basically, you apply the sim functor twice. So that is HM plethism HN, and the character is given by this form. So we can say that this R lambda n will be positive if and only if there is a partition mu with at most n parts, so that this product of plethism contains this Schur function. So this is the Hall inner product. This inner product is the Hall inner product that is just usually defined by it is the inner product of two irreducible of GLN. It is 1 if lambda equal to mu, either it is 0, and then you can extend this inner product to the whole space of symmetric functions. That is the usual Hall inner product. So we can say that R lambda n is positive if there is a partition mu such that this happens. So using this observation, we can give some sufficient condition. So basically, the first proposition says that if the difference of lambda 1 is lambda 2 is large enough, then I have positivity. And another sufficient condition is that if no two consecutive lambdas are odd, then also we have positivity. So for example, for n equal to 3, this is completely resolved. So W lambda C3 does not admit an string invariant vector if and only if B is odd and lambda is one of the following forms. So for n equal to 3, this is completely resolved. And one can do the same thing about the sign representation. You can take the sign representation of Sn and induce it to GLN. And the character of that is product of EMI plethism HI. So previously it was HMI plethism HI. But when you induce the sign, you just get EMI plethism HI. So all of this motivates us to have a crystal structure for this symmetric function. So what do I mean by crystal structure for symmetric functions? So can you give a Kashiwara crystal so that the highest weight vector in that Kashiwara crystal exactly counts the multiplicity of each Schur function? So let's recall the definition of Kashiwara crystal. So I'm just following the book of Bump and Schilling because there is some convention and I'm following that convention. So Kashiwara crystal of type A and rank N is a non-empty set B together with these maps. So these EIs and FIs are maps from B to B. So these are actually motivated from representations of B algebra where EIs are raising operator and FI are lowering operators. And there are two maps, epsilon I and phi is a map from B to Z. And there is a weight function from B to Zn plus 1. So this weight should be really thought of as the weight of the torus. And they satisfy these conditions that weight of y is equal to weight x plus the ith simple root, basically ei minus ei plus 1. This happens when ei x equal to y. That happens if and only if fi y equal to. And then when you apply ei, your epsilon I decreases and phi increases. So you can think of this epsilon I and phi as how many times you can apply ei and fi on a simple finite dimensional module. And there is one more relation between this Pi and epsilon I. The difference of Pi and epsilon I has to be equal to the inner product weight x comma the ith simple root. So a crystal structure for Hk that is already known. So usually the crystal structure for Hk is given by the one row semi-standard tableau. So what is one row semi-standard tableau? You just fill up some ones, then you fill up some twos, and then you fill up some threes. So I'm just writing that in a different notation. So in my notation, A1 is basically the number of time 1 occurs, A2 is number of time 2 occurs, and so on. And these are usual crystal operations. This is already known from this. And the character of this crystal is exactly the complete symmetric function in n variables. Now, one observation is that this Cmain of Cmain V that lies inside the mth tensor power of Cmain V. So what I am hoping for is that one can hope to realize the crystal for the plathism inside the crystal for Hn to the power n. But what do I mean by inside? So that I will actually explain by an example. So basically, some surgery can be done on the crystal graph of Hn to the power m, because Hn to the power n is just the tensor product rule for crystals. That is already known. The tensor product rule for that is basically Littlewood-Richardson rule that is known. So that is the thing. So maybe one can do some surgery on the crystal to capture this character, Hm plathism Hn. So here is one example. So this is the crystal structure for H3 square, H3 times H3. Now what is H3 times H3? That is just S60 plus S51 plus S42 plus S33. That is what is H3 times H3. So now I will make some observation. I have colored something. So so inside W51, for example, look at the vertex 2-1 tensor 30. But a permutation of 2-1 tensor 30, which is basically 3021, already occurs in W60. So I have actually colored all such vertex by the filled with red color. For example, see inside W42 there is 1-2 tensor 2-1, but that already a permutation of that already occurs inside W51, which is 2-1 tensor 1-2. So what I will do is that I will remove all the vertices which are filled with red color. So we are left with this thing. And my this is the crystal graph for this is in fact the crystal graph for H2 plathism H3. You can check, because after doing this operation, the highest weight vectors here are 30 tensor 30 and 2-1 tensor 2-1. What is the weight of 30? It is 3, 0. So what is the weight of 3, 0 again? 3, 0. You add them, you get 6, 0. That stands for A6. What is the weight of 2-1 tensor 2-1? That is 2, 1 plus 2, 1. That is just 4, 2. And that is in fact the Schur decomposition of H2 plathism H3. And this actually works for all n. By that I mean H2 plathism Hn. So this is only for H2. But doing this for H3 Hn is difficult. But yeah, I'm sort of trying to apply the same strategy. It's maybe possibly with some modification, because it's not that easy. In this case, this rule works. This will give you a crystal sort of crystal picture for the decomposition of H2 plathism Hn. And then what is the crystal graph for E2? Let's say E2 plathism H3. So you look at all the vertices, and two components are exactly same. So 30 tensor 30 2, 1 tensor 2, 1, 1, 2 tensor 1, 2, 0, 3 tensor 0, 3. So remove all these vertices. So then what you are left with is only these vertices. And what is the weight of the highest weight vector here? It is 3, 0 tensor 2, 1. The weight is just 3, 0 plus 2, 1, which is 5, 1. And 2, 1 tensor 1, 2, weight of this is just 3, 3. So that is in fact the true decomposition of E2 plathism H3, which is exactly S51 plus S33. And again, this works for any n. By that I mean E2 plathism Hn, but maybe for En plathism Hk, I mean that is what I'm working on. Let's hope for the best. And yeah, so another way to think about this induction, since we want to get into Kashiwara crystals, we are really looking for a module for the quantum group, because Kashiwara told us that any UQGLN module has a crystal base. So maybe to have a nice combinatorial theory, it is good to look into the UQGLN module structure. So another way to think about this induction module is to look at this space, 1 tensor CSN SND, where SND is the Schur algebra of degree D in n square variable. And this can be in fact quantized. So this CQ tensor HQN SQND, where HQN is the Yahoo-Heke algebra, which is the quantum deformation of usual symmetric group algebra. And this Schur algebra is a Q deformation. This Q Schur algebra is a Q deformation of the usual Schur algebra that is already known in the literature. And this can be defined because there is a one-dimensional character of HQN, which is given by TW goes to Q to the power length of W. TW is the basis of HQN indexed by the elements of S. And since this SQND that can be realized as a quotient of UQGLN, so SQND has a UQGLN module structure, and the basis of this space, this 1 tensor CSN SND. So how basically the basis of SND, what is that? That is basically the all n by n matrices with entry sum D. That is the basis for Schur algebra. But since you have this action of the CSN, so it basically permutes the rows of the matrix. So what you are really looking for, what we are really looking for is to have a crystal structure on this set, MND modulo Sn. MND is the set of all n by n matrices with entry sum D, modulo the permutation of rows. So if you can give a crystal structure on this, and that will solve the restriction problem. That is the thing. And indeed, from that paper of Narayan, Paul, Prasad, and Srivastava, we know that this character of this module is actually given by this sum, Pnx to the power x, where Pnx is the number of vector partitions of the vector x. And of course, you can think of the all vector partitions of a vector x as this set, the set of all matrices, but modulo the permutation. So finding a crystal structure on this would provide a satisfactory combinatorial interpretation for R lambda n also. So I am thinking from this perspective also, but I am more interested in this this kind of graphical operations that can give a crystal graph for that will be satisfactory for me at least. And just I want to finish by pointing out this thing. So remember this action we defined, action on the Lie algebra. So a quantum deformation of this action is already known, kind of. That is given by this formula, this thing. So here K lambda, EI, Fi, these are the generators of your quantum group UQGLN, and this quantized action is already known. And if you take Q tends to 1, we will get back to what I defined, what my action was there in the classical case. But the point is that to get a crystal basis theory, we need to go to Q tends to 0. So that thing that thing we do not know yet. So this deformation will give you this so-called A1 form of the high-straight UQ-GLN module. But for the theory of crystal base, I need A0 form, so which we do not know yet. We know the A1 form by this, but A0 form I do not. And yeah, so that's the state of the art. Yeah, I'll finish.
Any questions?
Yeah.
I can hear.
So you have a representation of GLN, and then you look at this representation as a module over symmetric group, right? So is there some expression for the character of this module as a module over symmetric group? So I mean, if you're interested in decomposition of some representation of finite group, right? So you know, character would give you something.
Yeah. So there is something, there is some expression in terms of the so-called character polynomials. So I think the same authors have a paper where they have a formula in terms of character polynomial, but that too in some special cases, not every case, not every lambda mu is covered. In some special cases, they have some character polynomial formula. But anyways, that does not help to give any positive combinatorial description. But yeah, there is some sort of, but that is again, that is a sign formula. It's like wild character formula. The wild character formula is usually signed, right? But people are interested to find positive combinatorial description. It's like that. Yeah. The correct analogy would be to say that everyone knows wild character formula, but it is signed.
Any other questions?